In this example, we have a disk, and the disk is pulled by this T force, which is 30 newtons, and some physical information about the disk is given, the mass of the disk and radius of gyration calculated about the mass center, which is g. We are assuming that this is a homogeneous disk, so the mass center is right in the middle of this circular shape. And the static friction coefficient and kinetic friction coefficients are given to us. Remember that at the moment we don't know if the wheel is moving without slip or with slipping. Therefore, we need to check the maximum friction force with the current friction force. If the current friction force is less than the maximum friction force that we calculate from this μs, then the wheel is rotating without slip. Then we don't need to use this kinetic friction coefficient. And that would be our first assumption in this question. We can assume that the wheel is rolling without slip and do our calculations with respect to this, and then check if this assumption holds or not. And how do we check that? By finding the maximum possible friction force by multiplying μs by n. N would be the normal force applied by the surface to this wheel. Okay. What else we have in this wheel? We have this gravitational force, which is m times g, and then there is this t force for pulling this wheel. And because of the location of this t force, it also generates a moment about this mass center, by the way. So we need to take that into account as well. This is not acting directly at the mass center, and as it is not acting directly at the mass center, it will generate a moment. mg will not, this gravitational force will not generate a moment, and will not generate a moment because it's directly passing through this point g. However, as we expect that this wheel is moving to the left, then our expectation is that wheel is rotating in the counterclockwise direction, and the reason that it is rotating in the counterclockwise direction is the existence of this friction force Fm. And we want to calculate this Ff and then check if this Ff, the friction force, is less than μs times n or not. If this is satisfied, then we say, okay, the wheel rolls without slip. And then what we are asked to find is the angular acceleration of the disk and acceleration of the mass center and friction force. All these actually have to be found during our investigation of the slippage. Okay, so what do we have in our hands to use is these three formulations. Two of them are from the vector equation of Newton, and then one of them is the moment equation that we would write about the mass center. So with the assumption of no slip, we can put our own frame. In this case, x, y axes are selected in this direction. Well, I would have selected in another direction. X would be in this direction, and then y would be in the downward direction. It would be a better choice for me. Actually, it doesn't really matter which one you choose, as long as you're consistent in your calculation. At the end of the day, you'll get the same type of solution. Now, the type of equations written over here actually shows that this is the way that the frame is selected. So x to the left, y in the downward direction. So if you take a look at these two equations derived from the Newton's vector equation of F equals to ma, in the y direction we don't expect any motion. We don't expect this wheel to jump. So it will be just moving in the same y level. Therefore, the motion, the resultant motion, is equal to 0. Then what we have is n. We can write this equation as n. If I use my selected frame, then it will be minus n plus mg is equal to 0. The right-hand side is due to the motion. because there is no acceleration on the right hand side, is equal to 0. And then you can rewrite this equation as N is equal to mg, and then calculate the normal force related to the mass and the gravitational acceleration. In the next equation, now on the horizontal direction, on the x direction, the type of forces acting on the system are this T force, which is 30 newtons, and then the friction force, which we don't know, F, some F. So we write it out as 30. This is the T force pulling it, and then F is in the negative direction, has to be in the negative direction because it makes the wheel rotate. Without this F, it will not rotate. There has to be a friction here to resist the motion so that it will act as a pivot point. So 30 minus F, and the resultant acceleration, which is something we don't know. So A is unknown, and the mass of the wheel is 25. So we have 25A. Now here we have two unknowns, F and A, and one equation. So we cannot directly find the solution here. We need a third equation because in the first equation we don't have any unknowns anyways. The third equation is our moment equation. This is the equation written about the mass center, and Ig is the mass moment of inertia about the mass center, which we can calculate as m kappa g squared. Kappa is the radius of gyration again. This information is given to us. M is given to us, so I can calculate Ig. Alpha, again, is something I don't know. But with respect to this assumption, assume that there's no slip, then A and alpha are related to each other. A would be equal to R times alpha. R is the radius of the wheel, and the radius of the wheel is given to us as 200 millimeters. So we have some information about this A. I can actually interchange this A with R alpha, and this is what's done over here. There's that information. 25 is the mass. This is kappa g Ig times alpha, and alpha again is related to acceleration directed by this equation. So I would not state this alpha as a new unknown parameter. So we have two unknown parameters still. On the left hand side of the equation, we need to take a look at the forces that will cause a moment about point G, and we already discovered these forces. These are T and F. N and mg would not cause any moment about this mass center. The moment that is caused by this T, with respect to our frame, the axis is going out of the board or screen, so it will be in the negative direction, and alpha, the way that we have it, is the positive direction. But in this equation, take a look at it, it's written as a negative sign here. So it is assumed that the z-axis is going inside the board, and the way that we write this equation is consistent with that. But if I want to be consistent with my own selection of x and y, then z is going out of the board, and as a result of that, this has to be plus, this has to be minus the moment that is generated by the t, and the moment generated by this f, due to the right-hand rule, has to be a plus. And as you can see, we'll get the same answer. Nothing will be different by changing the way that we define the frames, as long as you're consistent with your selection. Okay. Then, as a result of this, we have one unknown here. The second unknown, alpha, is related to A, the linear acceleration, and then F is the common unknown. We have two equations, two unknowns. Therefore, I can solve for alpha, F, and A, and then comes the point where we check if our assumption holds or not. How do we check that? We already calculated this normal force. Mu s is given to us. Mu s times normal force is the maximum friction force, 24.5 newtons. And then the friction force that we calculated from our motion equations is 18.38, which is less than the maximum friction force that can exist. Therefore, our assumption is correct. No slip occurs. Now, what happens if it didn't happen? What happens if mu s was half of this? Let's say 0.05. If mu s was half of that, then our assumption would not hold. So how do I change my equations in that case? The first equation about Fy would stay the same and would be the same. In Fx, would I change anything? No, I would not change anything, but then one thing would be known. F would be known now because F will be calculated by mu k, the kinetic friction, times N. And that would be the F in the second equation. And as a result of that, I can calculate the acceleration directly from the second equation. And after that point time, the third equation is the same type of equation. Nothing is going to change in here. F is known, therefore there's only one unknown. Alpha will be calculated. So linear acceleration and angular acceleration will be calculated independent from each other. They lose this dependency from kinematics. This relationship doesn't exist if we find out that slippage occurs. Okay, and this is the way that we would find the solution.